All right, let's go ahead and take a look at the warm-up here. So f of g of x, that means g of x is the inside function, and you're going to need to take it and plug it into the f. So g of x is x minus 2, and you're going to take that and you're going to plug it in. And something happens on this one. When you go to plug it in, there's actually an x here and here. So you actually have to put it in both spots. Okay, so I'm guessing that maybe some of you didn't know that and you only put it in for the first x, but you actually have to put it in for both of them. So it's going to say x minus 2 squared from when you plug it into this first x, and then plus 3, and then you're going to plug in x minus 2 for the second x as well. And then this is something that we could simplify, like we could FOIL the x minus 2, and we could distribute the 3 and combine our like terms. But really the thing I'm wondering about is this idea of substituting it in, and if you've got that down and if you're substituting it into the right place. So if you did multiply this out and simplify it, that's great, but that's not the part that I'm worried about. I'm just worried about, are you substituting it correctly? Okay. Then for g of f of x, we're going the other direction. So now we're going to take our f of x function and we're going to put it in for the g. So you want to take this whole thing and you want to put that whole thing where this x is. So then that's just going to be x squared plus 3x goes in that spot, and then there's this minus 2. And since everything is addition or subtraction, you don't actually need the parentheses, and so this would just be your answer. Any questions with that warm-up? Okay, find your page 401 work. We have 5 board problems to look at today. There were a lot of different ideas that we touched on yesterday that I want to make sure we go over. We're going to look at 11, 26, 29, 37, and 74. All right, so we're going to start with number 11. The functions were f was 7x plus 5 and g was x squared. And you had to do g minus f and then find the domain. The domain of f and the domain of g were both all real numbers. When you do g minus f, you're going to do x squared minus 7x plus 5. And that minus is going to distribute to both the 7x and the 5. So it should be x squared minus 7x minus 5. And then there's no square roots and there's no division. So the domain should be all real numbers. For number 26, it was 2x squared plus x minus 3 and x minus 1 were the functions. And both of them would have a domain of all real numbers. You had to do g divided by f. So I put g on top, x minus 1 on top, and then I put 2x squared plus x minus 3 on the bottom. And then to try to figure out what would make the bottom equal to 0, I factored the 2x squared plus x minus 3. And if you had me first trimester, I teach a method called the Xbox method for factoring when the number in front of x squared is something other than 1. So I did my Xbox work underneath of it. But if you have a different way that you factor that, like grouping or the 4-spot method or just guess and check, that's fine. But somehow you need to be able to factor that 2x squared plus x minus 3, and it should factor into 2x plus 3 and x minus 1. Then what can happen is the x minus 1s can cancel out, so your final answer would be 1 over 2x plus 3. For the domain, this problem had division. Anything that makes the bottom equal to 0, you have to exclude from the domain. And for the 2x plus 3, you would not want that to be negative 3 over 2, because that would make it equal 0, right? That's what the 0 of 2x plus 3 would be. So you don't want that to be negative 3 halves. You also don't want it to be 1. You have to make sure you do the restrictions before you cancel stuff out. That 1 would make it 0 on the bottom also. Okay, that one I think was a pretty challenging problem. So if you got it right, great job. And if you didn't, make sure you're fixing it and making note of it. We're not going to be testing on this concept until we come back from Christmas break. So this would be one of those things you want to star and make sure you look back on before we end up testing on this stuff. Question number 29, you had to find a composition of h of g of -2. So first I put -2 into the g equation, and that gave me -4. Then I took -4 and put it into the h equation, and that gave me 20, and that was my answer. For number 37, we had to do a composition of f of g of -2. So I took -2 and put it into g, and that gave me -5. And then I took -5 and put it into f, and I got 25 for my answer. The last one was number 74. I did go ahead and simplify these, and again, I'm not too concerned about whether you simplified them or not. I'm more concerned if you did the original substitution correctly. It asked you to do f of g of x and g of f of x. So first, for f of g of x, I took the 2x and I put it into the x for the f function. So it said 3, and then where it used to say x, I put 2x in parentheses, and then it was squared and then plus 2. If you do decide to simplify that, that squared has to go into both of those, so it becomes 4x squared, and then the 3 times is with the 4, and your final answer would be 12x squared plus 2. On g of f of x, you take 3x squared plus 2, and you plug that whole thing in for x, and you would use parentheses, and then to simplify, you would distribute the 2, and you get 6x squared plus 4. All right, I hope it was helpful to see those 5. And now we're going to go ahead and move into the next section, which is 6.7, which is on inverse functions. So we have inverse operations. Those are operations that undo each other, like addition and subtraction are inverse operations. We also have inverse functions. The way that inverse functions work is you start with a relation, which is any relationship between x and y, or they're going to use the letters a and b in these definitions. So a relation is any relationship that pairs a with b or gives you the point AB. And what an inverse relation does is takes that pairing and it switches it around. So in other words, you take all of your x's and all of your y's and you just switch their places. All the x's become the y's, all the y's become the x's. And then just a reminder, for something to be a function, each input has to have exactly one output. You can't have the same x going to 2 different y values. In other words, you don't want to have repeated x values with different y's. Okay, so we already talked about that when we were doing our prerequisite section, but that's just a reminder. All right, so here is a relation. It pairs 5 x's with 5 different y's, or actually some of them are repeats, but and the question is, what is the inverse of the relation? So for our inverse here, all we're going to do is make a new table, and we're going to switch all of our x's and y's. So the point 0, -3 becomes -3, 0. 1, 4 becomes 4, 1. 2, 2 is 2, 2. 3, 0 is 0, 3. And 4, -3 will become -3, 4. Okay, then I have some follow-up questions here. Is the relation a function, and is the inverse of the relation a function? So if I look at the original relation, I don't see any repeated x values. So I don't have the same x going to more than one y. So yes, the original thing is a function. If we look at our inverse, is the inverse a function? Well, the inverse has a repeated x value of -3, and it's going to two different y values. It's got -3 going to 0, and -3 is also going to 4. So no, that one's not a function. And then the third thing they want us to do is they want us to graph the relation and the inverse on the same axes. All right, so I'm going to use blue to plot the original function. So 0, -3, 1, 4, 2, 2, 3, 0, and 4, -3. And then I'm going to use green to plot the inverse. So -3, 0. 4, 1. 2, 2. 0, 3. And -3, 4. And then I'm going to draw in the line y equals x. And what I want you to notice is that the original function and the inverse function reflect over that line. In other words, each point has a corresponding point exactly perpendicular and across that line the same distance. And the one point that was on the line, 2, 2, stayed put because if you reflect a point that's on a line, it stays on the line. So all of our points reflect across the line y equals x, and it turns out that's true for all inverses, and that's an important fact for you guys to know. Inverses reflect over the line y equals x, always. So on the homework, you're going to have some problems that ask you to find the inverse, to tell whether the original thing is a function or not, whether the inverse is a function or not, and then they're going to have you graph them on the same axes so that you can see that reflection happen. Okay, the other idea for today is actually finding the inverse equation. So if they give you an equation, you have to be able to find the inverse equation. There's 3 steps that you're going to go through. Since an inverse switches all the x and y values, the way that we find an inverse is by switching the x's and y's in the equation. And then once we do that, we resolve the equation for y. And then they're going to ask us to determine if the inverse is a function or not. So after we complete our 3 steps, we're actually going to use something called the horizontal line test. So you guys know the vertical line test. The vertical line test is something you do to see if something's going to be a function or not. Well, the horizontal line test is something that we do to see if the inverse will be a function or not. Here's the thing though, you do it on the original graph. So you take horizontal lines and you put them on the original graph, and if they hit in more than one spot, then that tells you the inverse is not a function. So we do the vertical line test and the horizontal line test on the original thing. The vertical line test tells us whether the original thing is going to be a function or not. The horizontal line test, we do it on the original, but it tells us whether the inverse will be a function or not. All right, so the rest of the time we're going to be working through and finding inverses, and we're going to do a bunch of examples. And before we even find the inverse, I'm actually going to start by figuring out if the inverse is a function. So I'm going to start with the horizontal line test. And if we're going to do the horizontal line test, we need to know what this looks like. Now you might know what y equals x squared minus 1 looks like. It's a parabola, it's shifted down 1. But if you don't, then go ahead and use Desmos to graph it. Okay, so let's pretend like, I'm not sure if I remember what that looks like. All right, so I'm going to Desmos. Graphing calculator. Okay, y equals x squared minus 1. Okay, there it is, right? It's a parabola. It's got its vertex shifted down 1. All right, if I take that and I just do a quick sketch, down 1 is the vertex, parabola opens up, something like that. If we do the horizontal line test on that, it hits in more than one spot. So the conclusion is that when we get to our inverse, it is not going to be a function. So we haven't even bothered to find the inverse yet. I have no idea what it is, but I do know that when I find it, whatever it is not going to be a function, because I did the horizontal line test on the original thing. Okay, now let's go back and let's actually find the inverse. So step 1 said to switch the x and y. So if I switch the x and y, I'm going to have x equals y squared minus 1. Then the next thing I do is I just solve for y. So I have to get the y back by itself. So the first thing I would do is add 1 to both sides. It's going to give me x plus 1 equals y squared. Then to finish getting the y by itself, I would have to square root both sides. The square root and the squared would cancel out and give me y. And since I just put that square root into the equation, I need a plus or minus. So my inverse is y equals plus or minus the square root of x plus 1. And if you were to graph that, it would not be a function, right? Okay, let's try another one. We're going to find the inverse of y equals 3x minus 4, and we're going to decide if the inverse is a function or not. And let's start with that second part. Let's start by graphing y equals 3x minus 4. I'm hoping you don't need Desmos for this one. Three x minus 4, it's a line. It's a line with a slope of 3 and a y-intercept at -4. So down 1, 2, 3, 4. Slope of 3 means go up 3 over 1. That's what it looks like. If I try the horizontal line test, it's only going to hit once no matter where I put my horizontal line in. Since it only hits once, yes, the inverse will be a function. All right, let's go ahead and find the inverse. So step 1, we switch the x and y. So it becomes x equals 3y minus 4. Now we want to resolve this and get the y by itself. So I'm going to add 4 to both sides. X plus 4 equals 3y. I'm going to divide everything by 3. x over 3, that's like 1/3 x plus 4/3 equals y. That's my inverse. Okay, I've got a third example like this that I want to give you about 4 or 5 minutes to try on your own and see how you do. So instructions are the same. You're going to need to find the inverse, and you're going to have to decide if the inverse is a function. I would start by graphing the original thing and doing the horizontal line test, and then go from there. Let's say I've got 812 right now. Let's say we go over it at 816. 4 minutes to give it a try on your own. All right, let's go ahead and run through this one. So first, the graph, it's a parabola that's been moved right 4 and up 2 and opens up. Horizontal line is going to hit that twice, so the inverse is not a function. Then it's a little bit confusing because they substituted that f of x in, but I'm hoping you said, that's just like y. So now I'm going to switch my x and y. Right? So just pretend that this is a y, and when you switch your x and y, then it should say x equals parentheses y minus 4 squared plus 2. And if that threw you off, you can go ahead and fix it and then finish things out with me now. So then I'm going to subtract 2 from both sides to try to get my y by itself. So I've got x minus 2 equals y minus 4 squared. Then to keep working towards getting my y by itself, I'm going to square root both sides. That's going to create a plus or minus. So plus or minus square root of x minus 2 equals y minus 4. And then the last thing I'm going to do is add the 4 over. You can put it in front or behind the square root. I like to put it in front. So my final answer is going to be y equals 4 plus or minus the square root of x minus 2. If you wrote it as plus or minus the square root of x minus 2 plus 4, that's fine. Just make sure that it's clear that the plus 4 is not in the square root. Any questions on that one? Okay, the other ones in the homework are going to ask you to graph each relation and its inverse on the same set of axes. So if you're going to graph both of them on the same set of axes, the first thing you need to know is what they both are. So here I don't need to do that horizontal line test. It doesn't ask whether it's a function or not. It doesn't ask whether the inverse is a function or not. It just wants me to graph them both on the same thing. So I'm going to go ahead and start by finding the inverse. And then I'm just going to graph both of them. And if you know how to graph them by hand, you can. Otherwise, you can put them into Desmos and then sketch what you see on Desmos. So if we switch our x and our y, and then we resolve for y, we would subtract 3. And then we would divide everything by -4. X divided by -4 is the same as -1/4 x. -3 divided by -4 is going to become +3/4. So then the goal is going to be to graph y equals -4x plus 3 and y equals -1/4 x plus 3/4 on the same graph. All right, I think we can do those without putting it into Desmos. -4x plus 3, that would have a y-intercept at 3, and would have a slope of -4, so we'd go down 4 and over 1. So something like that. For the other one, y-intercept's at 3/4, so that'd be like about right there. And the slope is -1/4, which just means I could go down 1 and over 4 from my blue point. So if I go down 1 and over 4, I'm like over there. So this one's like something like this. Come on. And if we were to draw in the line y equals x, you can see how those are reflections over that line. Okay, I've got one more like this one to wrap things up for today. So again, instructions are the same. Graph each relation and its inverse. First, find the inverse. All right, so I switched my x and y, and then I had to square root both sides to get rid of the square. And since I put that square root in, I had to do a plus or minus. And then I subtracted 2 from both sides, and I just put the -2 in front. So what we want to graph is y equals x plus 2 squared, and y equals -2 plus or minus the square root of x. However, there's a problem. You're not going to be able to just graph a plus or minus equation. The only way to do that is to split those up into 2 separate equations. What this really means is one equation is y equals -2 plus the square root of x, and then the other one is y equals -2 minus the square root of x. So to graph that one equation, we're actually going to have to put 2 separate things into Desmos. And I don't think you guys know what those are going to look like, so we definitely want to put them in Desmos and see what happens. All right, so our original equation was x plus 2 squared. Parentheses x plus 2 and then squared. So there's the original. That one's a parabola that's been moved left 2. And then we want -2 plus the square root of x. So that one, interesting. That's just like, it's like half of a parabola, right? It's been turned on its side and it's just like half of it. So if we do y equals -2 minus the square root of x, that should give us the other half. So you need the plus or minus, because if you don't have the plus or minus, you're only going to get half of the parabola. And notice that if I was to put a horizontal line in here, it would hit twice, which is why our inverse is not a function, right? Our inverse doesn't pass the vertical line test. And if we throw in y equals x, just for good measure here, we can see how that's a reflection across. So then we could go ahead and we could sketch this, right? From what we're seeing on our Desmos graph, we could sketch it because the whole goal was to graph each relation and its inverse on the same graph. So if I come back to sketch that, it was basically left 2, there was a parabola, and down 2, there was a parabola. And then it was a reflection across y equals x again, something like that. All right, so for the homework, we're doing page 410, 9 through 27 odd, 42 and 43. You've got a little over 20 minutes of time right now that you could work on that. And then remember, tomorrow you're going to come on time by 7:40. I'm going to check in with you, take attendance, and then you'll have time to work. And that time to work could be on this page 410 stuff if you haven't finished it yet. It could be on any makeup or old work you need to do for my class, or anything else you need to do. And if you're 100% caught up in where you need to be, then tomorrow you'll be able to sign off and use your time how you would like to after we take the attendance and check in. This assignment is due tomorrow at 3 o'clock. So if you get it done right now during these 20 minutes, that's great.